All right. Well, hello. Uh, Thank you for joining Energy Modeling for Grid Optimal Buildings. Uh, Look forward to having people on this event. We've now passed over the magic 50 people threshold, and we're more than a minute over. So I'm arbitrarily saying, let's go. I'm Alexi Miller. I'm Director of Building Innovation at New Buildings Institute. I'll be moderating today. This webinar is being recorded, and it's on Zoom, so there are some Zoom tools. The recording will be posted afterward, and I believe attendees have access to either chat or Q&A. But you are muted, of course, and so are our panelists until they pop up shortly. This webinar was developed in partnership with the San Diego Learn program. It's a San Diego-based workforce education and training program. Learn has partnered with my organization, New Buildings Institute, and the Advanced Water Heating Initiative to offer a series of free energy efficiency and electrification webinars. There are some run by NBI, there are more. Please take a look at the Learn website for more info. Lots of good content on there. And today, pretty cool thing, we are co-hosting. We're trying to expand our reach here. This is also a Building Energy Simulation Forum event. The BESF is a group through Energy Trust of Oregon that focuses, of course, on simulation energy model type work on building energy. So Building Energy Simulation Forum, straightforward enough, also has a series of webinars, on-demand trainings, and those are available at the link on the bottom of your screen there, energytrust.org/commercial training events. There are several of these popping that are available here. You can see there are 5 specifically flagged as likely to be of interest for people who are interested in this event today. So feel free to take a look there. There is between the San Diego Learn and the BESF, there's lots of good content that's quite relevant. Today, we're talking energy modeling for grid optimal buildings. I'm going to give a very brief overview. I'm try to keep it to a minimum. My assumption is that a lot of the folks on here have seen the duck curve. I will not bore you again with another duck curve. We're going to have 3 expert presenters. I'm going to have Molly Kurtz from Pacific Northwest National Lab talking about demand response modeling. PNNL has been modeling DR events and building off of some really cool leading edge modeling of what happens when you do things like HVAC control modifications or other DR triggers in buildings. Think about what that means. What are the cost benefits? What are the other implications? How do we measure this stuff? And so I'll let Molly get into more detail on that. And then we've got Scott Spielman with Ecotope, who's going to talk about hot water, DHW, domestic hot water, how to model those. I'm going to talk about some results from real world buildings where Scott and team have put in central heat pump water heaters into buildings and have done load shifting research on those real world systems. So how much can you get out of load shifting? How do you do it? And then, of course, since we're talking modeling, going to focus on a really useful tool that Ecotope put together. It's available, freely available tool called EcoSizer, which is a really helpful tool for developing some of the key design and modeling inputs, like how big should this heat pump water heater be, and some of the other related questions that you're going to need to answer to design a system and to model it well. And then Neil Bolger with A2 Efficiency is going to bring us home, talking in particular about HVAC, but also a little bit more broadly, talking about how do you actually model HVAC system load shifting. Are we asking the right questions? And we'll flag some useful solutions and some content and some interesting research outcomes that Neil's come across. And then we're targeting plenty of Q&A time to follow. Unusually for this series, it's a 90-minute session. Thank you to Scott Spielman and Molly, not only for agreeing to present today and share their expertise, but also for agreeing to present for longer. So we're hoping to have about an hour of presentation time and about 30 minutes of Q&A time. We'll have a presentation, and then we'll give a couple minutes for just clarifying questions, sort of straightforward questions for the presenter, each in turn, Molly, Scott, Neil, and then save the really interesting conceptual or more thorny questions for the end, jot it down, because then we can have more of a panel discussion at the end. In terms of overall context setting, I'm just going to say a couple of quick words. There are multiple words for things like GridOptimal or GEB. GEB is an acronym we might come across: Grid Interactive Efficient Buildings. That's commonly used by the US federal government, among others. When I say GridOptimal, I mean Grid Interactive Efficient Building, just as much as I mean GridOptimal. The particular words are not too critical to me. But the concept, I think the key concept here is that we're talking about buildings that are both better for the grid in terms of their passive energy use. So they have lower coincident peak demand, for example, which is to say they're less peaky when the grid is peaky. And so that's like the passive stuff, right? A very high efficiency building is often a better grid citizen just per se, right? Like that, because it's got a much lower grid, it's easier to, or peak, it's easier to serve from that, from the grid on which it sits. But also there's the flexible side. So there's like the passive side and the active side. The flexible side is a good grid optimal building, or a GEB, also has some flexibility, some capability for flexibility in the building. So that might be able to take a signal and do something with it. It might be able to take a demand response signal and adjust HVAC set points, or shift load on the water heating system, or take other strategies. The point I'm making is that when we're thinking about building grid integration, there are multiple ways that you can achieve that, and it could include both passive strategies that are what we commonly think of as efficiency, and active strategies that are what we commonly think of as demand response. They conflate, and they can be interrelated, and so we want to think about holistic solutions, which of course can be tricky to model. So here we are, right? Those holistic solutions require sometimes a little different modeling. With that, I'm going to pass over to Molly with Pacific Northwest National Lab. As mentioned, then we'll go to Scott and Neil. So Molly, I'm going to stop share and allow you to take over.
Okay.
Thank you.
Can you just confirm that you can hear me? It looks like one participant is having trouble with audio. Just want to make sure.
I hear you loud and clear myself, yes.
Hopefully everybody is good on that then. Let me share my screen. All right. My name is Molly Kurtz. I'm with Pacific Northwest National Labs. I'm in the Seattle office. My presentation is about load management and demand response energy modeling work that we've done here at PNNL. And I want to make sure that I recognize my colleagues Lingzhou Wang and Jen Zhang, who have been collaborating with me on this work, and especially the specific modeling analysis that I'll show is primarily Lingzhou's work, but he is away on vacation, so I am presenting on his behalf. So I want to make sure to recognize them for their contributions. So I want to start off with like a brief context setting of PNNL's work in using energy models for analysis, talk about some specific sort of high level, or talk about rather some high level concepts on modeling considerations when modeling load management and demand response measures, and then present some specific modeling analysis that looked at surface water heating, thermal energy storage. And then I want to close with some general observations that from the work that we've done so far. So for background on PNNL's work with energy modeling and codes analysis, we maintain the 16 DOE commercial building prototypes. These are prototypes of, quote, typical buildings in the US that are used to understand over time the development of building energy codes, and also cost effectiveness of those code measures in typical buildings. So when a model code has a new update, PNNL always does a determination analysis for Department of Energy to assess what are the energy savings impacts of that new version of the proposed code, and what is the cost effectiveness of those changes. So in addition to looking at cost effectiveness for DOE, we also provide support for the code development process to standards committees. So that can be the model codes committees as well as other ASHRAE committees that our my colleagues support. So one of the, moving on to kind of the high level things to consider when doing an energy modeling analysis of these types of grid interactive strategies is the first one is kind of how are you going to quantify benefit of the measure that you're attempting to model. I want to talk about some differences in my mind between demand response and load management. And how I'm using those two different terms, and then also some considerations for occupants' experience and level of service to occupants. So starting off with metrics, I would say traditionally our analysis at PNNL looks at energy consumption and cost savings associated with that energy consumption. So a straightforward transition when we're looking into load shifting or load shedding is considering instead a time of use tariff. We could also think about looking at a demand response program where you might be compensated for your load shedding or paid on a flat rate for participation. We could think about doing some sort of time of use carbon-based metric. That's certainly an option. We need to develop what that metric is if we're going to tackle it. And then another option might be to think about looking at quantifying the curtailable power and duration of curtailment. And so for that option, maybe we don't need to get so much into the simulation details, but it's still possible we might want to do some simulation to validate the performance of different measures with that approach. So moving on to the distinction in my mind between demand response and load management, I think of demand response as being directly responsive to a utility request. And again, you could be compensated for participation in the program, or you might be compensated based on your performance in that program. Load management, on the other hand, I think of as more managing your power and energy consumption to perform under a time of use tariff in order to reduce your energy cost. So just to put this, what I'm going to present next into more context, PNNL has done all of our load management analysis using this time of use rate, which I'll tell you more about in a minute. But we really haven't developed a nationally representative demand response program model or tariff model to support analysis. So that's something that we may need to look into developing. And then lastly, I want to talk about occupant level of service before I get into some more details. The occupant level of service is pretty important to bear in mind when we're looking at assessing these measures, because what we don't want to do is, you don't want to, ideally a demand response program, the occupants will not have any notable impact on their experience. But if we're analyzing this with a time of use rate, we need to be careful that we're realistically modeling development of this of a measure in a real world condition. And so for example, if we're dimming lights, we want to make sure we're not dimming lights for all of the peak hours for the entire year. We have done some initial analysis looking at dimming lights with the time of use rate and got feedback from the committee, well, that's a little bit too much. Like we're thinking more of a demand response event happening, several times a year or once a month, but not you're dimming your light for thousands of hours per year. So just wanted to flag that as something to keep in mind if you're doing this type of analysis, really think through whether the scenario is realistic. So the time of use rate that I mentioned to you was developed by the 90.1 Economics Working Group Committee in the summer of 2019. This was developed using by surveying national time of use rates and then coming up with something that that group felt would be reasonably representative of a national typical approach to a time of use rate. So obviously not something that can be averaged over the nation. Each local utility may have their own rate. So that's another challenge here. But in order to be able to quantify energy cost benefit associated with load management, this was the approach that the committee endorsed. So these are those rates visually for the winter period and the summer period. The winter period on the left, you can see the red shading is the two peak duration periods. So there is a morning and an evening peak for the winter versus in the summer. On the right side, we have only one peak period, but it's quite long from 1 p.m. until 9 p.m. in the afternoon. There is a year-round base demand charge, which is at $5.18 per kW. And then in the summer, there is an additional on-peak demand charge at $10.18 per kW. So, and then this formula is just showing the monthly calculation of the utility bill based on those different energy and demand factors. And so the max peak kW will be in addition to the base kW charge with this rate. And then I wanted to flag that for any analysis that you're doing that's energy modeling based, you're going to need to define what you mean by a peak demand. And that is to say, is it an instantaneous demand? Is that an average demand? And if it's an average demand, what's that averaging window? And I'm just pointing out here that if you have a 90 kW peak for 1 minute, that's a high value, but if you're charged based on a 15-minute average demand, that becomes only a 6 kW over that 15-minute average. So make sure you're thinking about that issue. And then on the simulation side, if there are practitioners here today, you want to make sure that your simulation time step is coordinated with that demand window so that you can do those calculations correctly. Okay, so now I want to move into talking about some specific modeling analysis that Lingja led on the surface hot water thermal energy storage. So we used the DOE commercial building prototypes and the ASHRAE time of use rate as the metric. And then we looked at 3 different control strategies for doing thermal energy storage with surface hot water systems. And a couple of things going into this discussion. First of all, we needed to make some adjustments to our prototypes because many of the prototypes use natural gas for water heating right now. So we revised those to ensure all of the systems were using electric surface water heating so we could do this analysis. And then we also reviewed and revised some of the storage capacity for those water heaters. So this table is just showing the storage and heating capacity for the different prototypes that we ended up going forward with, and this is fully electric for this analysis. Okay, so the control strategy that we looked at included 3 different controls approaches. So, but all of them were fundamentally looking at, well, our baseline condition was 140 degrees all the time was the aquastat temperature for the tanks. And we looked at 3 different variants of that. One was to have a step control where we would have a 6-hour preheat period prior to the peak period, and we would heat the tank up to 180 degrees during the preheat 6-hour period. As soon as we reached the peak period, the aquastat dropped down to 120 to discourage the tank from firing or the element from engaging during that peak period. And then for periods that were not peak or preheat, we put the tank at the baseline 140 aquastat set point. So I'm going to walk you through the analysis, hopefully fairly quickly, but just the 3 different approaches we took were kind of that step approach. And we did a variant that was a ramped approach on the aquastat, which is shown in the orange line on these graphs. And then lastly, we did a customized approach, which was a little bit of a variant of that ramped approach. So I'll take you through that analysis here now. So first looking at the step set point schedule or set point approach, we did find that this did have some energy cost benefit, but one thing that we found at times, which you can see on the right-hand graph that's circled as area 3, is that we ended up with these big spikes of demand during the preheat window when we had set the thermostat, the aquastat set point up to 180, that the tank was firing at full bore during that time and could cause a building peak demand, which was impacting the bill for that month. So that was an issue with this control strategy. We found on average across the prototypes that we looked at and the climate zones that we looked at, there was a modest cost intensity savings of 1.3%. So that was the step set point. We then looked at this ramping approach, which is the orange line, as a means of trying to mitigate that issue that we found with the higher peaks during the preheating period. So I'll show you those results now. The cost intensity savings percentage did increase from our 1.3 to about a 1.8% across prototypes and climate zones. We did successfully mitigate that sudden spike that we were getting, the demand spike during the preheat period. And so that was a positive, but we did find that in some cases, here's an example, the left-hand side is showing the step schedule and the right-hand side is showing the same prototype, same time for the ramped schedule. But we're seeing it's circled as 0.2, the higher demand during the preheat time. And that's sort of on the left side, we have this big spike right at the beginning when we first set the aquastat up to 180. But in the other case, we have the ramped schedule. We don't get that big spike right at the onset of the green preheat period, but we still found that subsequent spikes were higher than the spikes we had on the left. So it kind of has to do with the alignment of the overall building electrical load profile and the control of the water heater and the firing of the water heater.
Hey,
So that
Molly, just a quick note. We got a note from someone in the Q&A saying you sound a little faint. Maybe I hear just fine. Some other folks said yes, same, but maybe you could hold your mic a little closer to your face and
let me see if I can do. Is that any better? Is that helping at all?
Well, it sounds louder.
Speak up. Okay, I will try to speak up. I think it's
All right.
using my laptop mic, which was off on the side, so maybe that's part of the issue, but hopefully that helps.
Okay. Yep.
Okay.
Same thing says yes. Thanks. Appreciate
Okay,
it.
cool. Sorry about that. So, yeah, so then that observation was sort of led us to this approach of using, maybe we could get a better savings if we used a customized set point schedule, which is based on the ramp schedule, but we made some changes depending on how that was interacting with the overall building load profile. So, for example, if we found that the storage that was the stored energy in the tank wasn't enough to make it through the entire significant peak period, which was like, I think 9 hours for the summer peak time of use schedule, then we might adjust the point at which the Aquastat set point dropped till later in that period and still see a benefit of that. So that's what's shown here on this graphic, that we're actually extending the 180-degree period out to the 1600 hour, and then allowing the set point to drop down to 120. And we are achieving a reduction from the blue line is showing our original constant set point at 140, and then the orange line is showing our demand with the step set point. So with this sort of customized approach, we were able to improve the overall performance of these different building prototypes by tailoring the controls really to what was happening in each model. So I'm gonna skip over that slide and then say that with this approach, we did get a little bit more savings on average. So 2.1% average cost intensity savings. We still did find that there were cases where we were getting a higher peak with the optimized, or not really optimized, but with our control strategy compared to say the ramp approach, and that's what we're showing here in this graphic. So for climate zone 2A, this was the apartment high-rise prototype, and we found that we got less of a reduction using the customized compared to the ramp. We had a lower reduction of peak KW, at least for this day that's shown here. But generally speaking, we got a better demand reduction with the customized approach. But the conclusion here is that really sensitive to different control strategies, sensitive to how that control aligns with the overall building load profile, what else is going on in the building besides the surface hot water power requirements, which makes this very complex to capture in an energy modeling approach. To wrap up, some kind of general observations and conclusions on what we have done so far. So for load management modeling of surface hot water, as I just said, it's very much less predictable than using an energy model to assess an energy efficiency measure. It's kind of sensitive to the strategy that you're doing, how you may control it, what else is going on in the building at the same time that doesn't have anything to do with the equipment that you're controlling. So those are all factors to think about. Another issue is to think about the time of use rate may or may not align with, oh, sorry about that, may or may not align with high emissions hours on the grid. So sometimes those time of use rates are designed around transmission and distribution constraints rather than being well aligned with emissions. So that's an issue to consider. for codes development in 90.1, the load management requirements kind of stipulate one of the following. You can have a demand response program, you can have real-time or next day pricing, you could use a time of use price schedule. And I guess our comment on that is that not all three of those are the same. And so there is some nuance there in how we may assess the benefits or analyze these types of measures. Then on demand response modeling, again, yeah, just thinking about how is it best to measure these benefits or quantify these benefits. We don't have this national average demand response payment program model. So maybe is that something that needs to be developed? Do we quantify this in some other way other than owner cost, energy bill benefit? Should this be quantified in terms of, some other societal benefit rather than an energy bill assessment? So, and then perhaps maybe we just need to look at peak KW reduction, and maybe there's less modeling based analysis to support that. And then secondly, if we are going to simulate demand response, how should we simulate that signal? How many times per year? How do we consider the grid peak load and the building peak load alignment or misalignment when we're doing that analysis? And that the time of use, peak time can be used, but is it the best metric to use? So we're still kind of working through those discussions and considerations, and do think that we probably have more development and thinking to do going forward on how to assess demand response measures for code analysis. And that's what I have for today. Thanks very much.
Thank you, Molly. We got a couple of questions. For the most part, I'm going to hold till the end. I do want to ask one quick clarifying. Can you go back up? I think it's slide 7. It's the one that shows the time of use rate structures.
Yes.
There was one question about regionality, but I think that those are national rate structures, sort of national average for ASHRAE use, determination use, right? And it's really, those are just time of use rate. If you go to the next slide, that shows, the delta from sort of almost baseline to propose, right? Like this is where you save your money. And so when you're talking about a 2% savings, it's because you're reducing usage during these relatively expensive peak times. There's no dollars per kilowatt hour, dollars per kilowatt of demand response program incentive, which is relatively common and often outweighs this time of use rate savings. So that I'm sort of conflating 2 or 3 questions here, but I just want folks to be clear that these are national average, pretty conservative, tiered time of use rate cost assumptions, and it's not the demand response program, which is probably a large part of why we're seeing this. 2% energy savings. It doesn't seem dramatic, but it's because we're taking this very conservative assumption up front.
Yes. Also, I should clarify that those savings amounts were kind of just showing like the relative values from the 3 different control approaches that we used, and that very much big variation I didn't show you the full results, but depending on the building use type, for example. So in a multifamily building with very high water heating use, there was more savings than in a low, a building that has a much lower capacity, much lower KW of water heating. So like you shift your KW of water heating to off peak, but you don't have very many KW of water heating if you're an office building compared to, say, a multifamily building. So I should mention that as well too.
Sure, there's less to shift.
Yes, yes. Yeah, so those are the results that I shared were very not very specific to provide much insight, but just showing sort of relatively for the 3 control strategies what direction did it move in.
Yeah, makes sense. Thank you. Well, let's get a little more specific about hot water systems with Scott Spielman. Scott, I believe you can just share and take it away.
Awesome. Thanks, Molly. Thanks, Alexi. I'm going to just share my screen here. Okey-doke. How's that look?
Looks good.
Okay, great. So I'm going to talk about modeling commercial heat pump water heating systems, both from an efficiency perspective and a load shifting perspective. A little bit of background about me. I'm the Director of Technology Transformation at Ecotope. Ecotope is a mission-driven engineering firm focused on providing emerging technology solutions for decarbonization to counteract the climate crisis. And we've been focused on heat pump water heaters, especially in multifamily buildings, as one of the last areas where gas is still used very heavily and a high percentage of load in a really important building type that is a high percentage of the building stock and being constructed rapidly right now in a lot of different areas. So one of the things that's nice about hot water systems is we've got a large thermal storage volume inherently built in, especially when we're using a heat pump water heater, because when we design with a heat pump water heater, we can add to the storage volume in order to provide less capacity on the hot water generation side from the heat pump. And that both helps the heat pump from an operational standpoint because it has a more stable, long period duty cycle, which is beneficial for the longevity of the compressor in the equipment. And it helps us with load shifting because that large thermal storage tank can be a thermal battery that we can use to shift load. So in this diagram here, it's kind of like a schematic diagram. We show that hot water usage shape in the light blue solid line. And then that load shift dash line is a representation of what we're trying to get to on the electrical side when we shift load. So if we wanted to shift load away from morning peak and evening peak hours, those line up perfectly with when hot water is used. But because we have that large thermal storage volume, we can shift when electricity is used to just before those large peaks. So although I'm going to be focusing this presentation on modeling, a lot of Ecotope's work has been on demonstrating these technologies, bringing them to market and demonstrating them. And we've got over 20 commercial heat pump water heating sites in the field that we're actually monitoring the performance on right now. About a half dozen of those, we are either doing load shifting controls and assessing how well those load shifting controls are working, or we are in the progress of setting up load shifting controls so we can assess how it works. I'm not going to get into a ton of the detail on specific installations, but rather talk a bit more about the modeling tools that we've developed that have been a result of our findings on these demonstrations. Just to kind of tee up a little example here as far as high level what savings are coming from efficiency versus load shifting when we go from electric resistance to heat pump. I really like this plot here. This is from Bayview Towers, which is a low-income 100-unit multifamily building in Seattle, Washington, where we piloted a load shift capable heat pump water heater that uses CO2 as the refrigerant. And the blue line or the blue bars are what the energy consumption during the morning and evening shed periods would be with in-unit electric resistance heaters. So if each unit just had its own electric tank, we'd be using about 70 kilowatt hours during those 2-3 hour periods, just from switching from the in-unit heater to the heat pump water heater with no control, no load shift controls added, just switching what is providing the heat. We save about 60% of that peak demand. We reduce that peak by about 60%. And then when we add the load shifting controls, we were able to take that energy consumed during those peak periods down to almost nothing. Got very close to, below 10 kilowatt hours used in below 5 really kilowatt hours used in those shed periods. So this is just a good demonstration of just the energy efficiency technology gets you a lot of the way to reducing the peak, and then layering on top of that, the load shift controls can really bring the rest of the peak reduction into the picture. As far as modeling efficiency, if you're looking for just a quick COP value that you can use to look at an annual savings from a heat pump water heater versus a gas or electric resistance system, I'll recommend that you look at the Northwest Energy Efficiency Alliance qualified products list. There's a qualified products list posted on their website. You can look at the PDF, and it has a couple hundred of these fully systems from different manufacturers and distributors where the annual system COP, so that's not just the COP of the heat pump itself, but it's the whole domestic hot water system to provide the recirculation heating and the primary heating of incoming cold water. That would align with the way that the manufacturer distributor is providing the system. And you can take that system COP and get a quick assessment of what the savings are going to be on an annual level. The hot, mild, cold, and very cold climate zones are defined in the advanced water heating specification, as well as the methodology that was used to come up with these system COP ratings. And they're based on the ASHRAE climate zones, but just grouped a little bit more broadly. So we have the 2 of the hotter climate zones grouped together and 2 of the very cold climate zones grouped together. The way that those system COPs were calculated is written up in the advanced water heating specification, but it is also in the product assessment datasheet spreadsheet, which is what manufacturers who are listed on the qualified products list, they download that spreadsheet, they fill it out, put information on their system, what components are in their systems, and their performance map. So this shows a performance map at the bottom of this screen, which is just at different ambient conditions and inlet and outlet water temperatures, what is the input power and output heat provided by the equipment tested. These performance data points in that pad spreadsheet are used to calculate the system COP at the different climate zones outlined in the advanced water heating specification and qualified products list. And if you wanted to do a more detailed assessment of how efficient a particular water heater would be at a specific location, you could download the spreadsheet and just modify it. It's not password protected or anything like that, so all the calculations are open in there. It's a bin calculation with some added factors that were developed based on lab testing that was done in a lab, the Pacific Gas and Electric lab in California. But the spreadsheet is very transparent, easy to use, and it's available for anyone who wants to download and use it. You can also get the performance map information from the manufacturers by just clicking on, I don't know if you can see my mouse, probably not, clicking on the link that is in the identifier. That's a URL link that will take you to the PADS spreadsheet from the manufacturers filled out so you can see the performance map.
We do see your mouse.
Okay, cool. Thanks, Alexi. So that was all Northwest Energy Efficiency Alliance tools. And now I'm going to just shift over a little bit to EcoSizer and the tech program calculator that we developed for that program in California. So EcoSizer is an online sizing tool for sizing heat pump water heating systems. And we took the backend code that is used to do the system sizing, and we extrapolated it out into a simulation tool that simulates the operation of a system over the course of a whole year. And for the tech program, compares with and without load shifting controls, calculates the CO2 emission savings, and tells the user whether the system qualifies for a tech program incentive and what the load shift capacity would be that they could get incentivized. So the way the simulation works is you've got to enter a zip code, which just gives you the location of the building, which is used for the weather file, and the CO2 emissions data, and then the size of the building. For the tech program, this is limited to multifamily buildings, so we're putting in the number of apartments with different 1, 2, 3 bedroom studio. So just plugging in that basic building information, and then that building information gives us information on what the load of the building will look like. So how much hot water is used on a daily basis. And so we've got a 8760 load profile that we put in the simulation, along with the 8760 hours in a year, CO2 emissions, and weather data. Then you'd select the system type. So we've got the single pass or multi-pass system, and then the temperature maintenance system configuration, which is how the recirculation is piped. And these align with the standard configurations defined in the Northwest Energy Efficiency Alliance Advanced Water Heating Specification that's also referenced in Title 24 and as the best practice for installing and setting up heat pump water heating systems. After you've got that information on the building, the location, and the system, you would select the heat pump water heater model. And this, from the heat pump water heater model, that's where we get that, we pull in the performance map data, which shows the efficiency, the power input, power output, heating output over the different outer air temperatures and inlet and outlet water temperatures. And then just specs on the system that you're installing. So whether it's 1, 2, 3, 4 heat pumps, how many gallons of primary storage, and then information on your temperature maintenance system if required. So the workflow for this would be the engineer would size the system using the main EcoSizer page. They'd select their equipment, and then they'd go into this tech program page and they'd put that data in when they're looking for the simulation to show their incentives. And then finally, last but not least, we have the load shift controls. And these are really important. This is just we need to know in order to simulate how the heat pump water heating system is going to adjust its operation based on requests from the utility or just based on time of use pricing if it's a fixed schedule. So like Molly talked about, there's a load up period where she was showing a stepped function that PNNL modeled and a shed period where that set point was dropped. The way that we've been successful doing heat pump water heaters in the field is a little bit different than just set point control. It's a little bit more complicated. The storage volume is larger. So we use what we call aquastat staging. And basically all that means is that we change the location of, we have multiple temperature sensors within the thermal storage tank. And then we change which one we are referencing to turn on and off the heat pump, or which ones we are referencing to turn on and off the heat pump, based on what operating mode we are in. So if our operating modes are normal, load up, and shed, in this case, in normal, we're going to be turning on at a temperature sensor that's 40% above the bottom of the storage tank, if we're just with one storage tank. In load up, we're going to turn on at a temperature sensor that's 20% up from the bottom of the storage tanks. So in the load up scenario, we are pushing heat from the top of the tank down further in the tank and storing more heat in that thermal energy storage system. And then in shed, well, also in load up, we can adjust the heat pump water heater outlet temperature, so we can inject hotter water into the top of the storage tank to increase the density of our thermal storage as well. And then, sorry about that. And then in our shed, we, instead of referencing that 20% temperature sensor, we move that up to 80. And now this is just allowing our storage tank to drain more of the hot water out, and it allows us to ride through a longer period of time without needing to turn on the heat pumps or any other electric heating sources. So then when you hit run, simulate, in the tech program page, this is what it gives you. It shows you the average shapes for energy usage with the baseline heat pump in red, which is no load shifting controls added, and the load shift controlled heat pump in blue. And you can see how those lines look different. You can see a spike for the load up happening for the on that blue line, and then you can see the shed happening where it goes to 0 during that load shift period, which is shown in gray. And the metrics calculated at the bottom are for the tech program. So in this particular run, we were saving 960 kilograms of CO2 emissions per year. Our load shift capacity, which the load shift capacity is just calculated as the amount of hot water that can be discharged between the load up state and turning off in the load up state and turning on in the shed state. So it's just essentially how much heat can that thermal battery release without having the heat pump need to turn on. And that's calculated into this kilogram CO2 emission per kilowatt hour load shift capacity, which is a value that's used in the tech program, must be greater than 5 to quantify or to qualify. So just a high level overview of some of our inputs: system configuration, performance map, the controls, the annual load shape of the building, and then the conditions which the heat pump is operating in. Some stuff that we would like to include, but we didn't have enough information, is in the simulation tool is defrost characteristics. So how does defrost impact the heat pump output capacity and energy usage in those lower ambient, high relative humidity conditions where defrost occurs, and stratification profile. Right now we have a pretty simplistic model for stratification, but we'd like to do some research to put a more robust stratification model into EcoSizer to get more accurate values. These are just some links to some different research that we've done on both stratification and defrost, thermal storage, and defrost. We've looked at those thermal storage profiles and how they react with different tank piping. We haven't built those into our EcoSizer engine yet. And then some defrost analysis from some of our demonstration sites. Something that I want to note is that EcoSizer engine, which is what is the back end of EcoSizer, is open source. It's pip installable. So if you're a Python user, you can easily install EcoSizer engine and use it for custom analysis. And all those equipment curves are going to be built in there. So you can just use, simulate different systems with different controls for your modeling purposes. Here's an example of a way that we use that backend simulator to understand the impact of storage and capacity on the load shift capability with a market rate load shape and a low income load shape. And we just simulated less storage, more capacity to more storage, less capacity with the same load shift controls. And you can see kind of as we move down there, we get a higher percentage of success rate on being able to shift load through the entire shed period. And yeah, all this work wouldn't be possible without some of our partners. Northwest Energy Efficiency Alliance, Bonneville Power Administration, NBI, all the other folks listed on this page. It's just been really allowed us to successfully dig into the technology, validate things, and develop tools. And I think that is it. Yep. Thank you.
Thank you. Thank you so much, Scott. We'll save the questions on this one till the end, but I do want to ask you one favor. While Neil is presenting, if you would be so kind, would you be willing to take a look through and compare to the chat and see if there are any links that folks might use that are not yet in the chat? I think there's been some requests for links. Most of them are in the chat, but if you could just take a look and say, oh yeah, here's this, here's that.
Sure. Yeah, thanks.
Without further ado, Neil, you're up.
All right. Thanks, Alexi, and thank you, Scott, for that great, and Molly for the great preamble presentations. Very excited to be here and share a bit about some grid optimal strategies we think about in the world of HVAC, right? So in heating and cooling in the buildings, all very related though. So it's always exciting to get to go last. I can see what comes before this. I will say I was deleting slides in anticipation of our clock ticking, so I will try and keep us on time so we have some conversation.
Awesome time.
All right, so just a quick overview of what I'm going to share today. My name is Neil Bolger at A2 Efficiency, a small consulting firm. We do a lot in the space of energy modeling, but also design practice with building designers, and then research helping support policy, codes and standards enhancements, program enhancements. So you'll see some of that kind of come through. But today, in thinking about what Alexi asked me to talk on, I want to just kind of reiterate what I see as like the problem or the challenge right now of energy modelers out there trying to figure out how to design grid optimal buildings. Give an example of where we've had some success in trying to frame problems and bring those problems to light with our clients, and for them to then articulate, what do we do about this? Should we change how we design our buildings? And then share a little bit of current research work involved in today around thermal energy storage, which ties back to everything we've been talking about that we just saw from Scott. So kind of my own little diagram here that I almost made for myself to just mentally unpack all the electric connectivity that's needed to support building thermal loads, right? We have all this infrastructure up to the meter and then even beyond that's really required. But when I really think about loads, even in some of the research we're now doing, I kind of take it apart and think both about the gains themselves, leakage from the envelope, air leakage, solar gains, and then once we turn that into hot air, hot water, what are we doing with it? When are we operating those systems? How can we shift those systems? But by and large, just a couple of quick slides, it kind of goes without saying, but the challenge I think that we're really in is like energy modeling community is this, we're stuck in like an annual mindset, right? I can very well articulate what I think an EUI might be, where the elevator EUI might be for annual energy. It's very hard to sort of build that industry knowledge around, well, what should we anticipate the peak demand challenges are of these systems? Which one might have more of a peak demand that I need to consider? And then how do I account for that in my models? A lot of our modeling paradigm, as I call it, is sort of built around some default libraries, right? These are sort of default assumptions that are a lot of energy modelers will just get and pick up and run with, and they do not have a ton of time to then change them to maybe be more dynamic. And a lot is changing, right? We now live in a world post-COVID. Buildings aren't used the same way they used to be used. And it just presents a bunch of these challenges when we start to ask, well, what's happening at this time in my model or at this time on the grid? A fun, again, diagram that I kind of made for myself as a thought experiment. I was looking at all this conference room data and just laughing about how all these conference rooms I was measuring in a real building were in heating mode when it was 55 degrees outside. And how when we look at energy models, a lot of times people will just jump to the default assumptions that a conference room that's 200 square feet might have 7 bodies, they all need fresh air, they have a bunch of lights on, and everyone has a computer. So, you know, those sets of assumptions that we're sort of using based on these like libraries of tools we've built would say that that room's in cooling, when in my life I've been in a lot of conference rooms where it's me, one other person, and maybe we have a shared phone, right, that's going on. That room's in heating. Very different results. And so it's just sort of reinforcing this challenge of like assumptions matter when we're starting to study these grid optimal problems. There are some tools, I can add this link, but this is an old tool that still is really useful. And I think maybe having in my own work, a revitalized purpose, but this tool LVNL made a while back, just this dynamic scheduler. It was built around offices. I think there might be a few other space types, but you can go in and say, how many people are there? Do they take lunch? Do they leave? Do people visit? It will take your schedule, give you a more spiky schedule. So again, not that everything should be random and finite, though there are some tools out there that are trying to come into the annual simulation environment and make our models a little bit more able to predict the grid peaks. Okay, but what I really think of is this challenge that I think the best way I like to frame it is for each project, you almost need to develop your own grid anticipated problems. In HVAC, there's almost too many things that could change that. For me, I bring it back to the project and ask questions around like, is there electric resistance heating in the site? Could there be in the systems we're designing? And then asking just questions about the building usage. When do we anticipate cooling happening? You know, other basic things that I think we've all asked for years internally as we're making models that were idealistic on how they work. So now it's becoming more critical that we can point to them and say, well, this assumption actually might have a big impact on the outcome. So I would say, like, as experts in knowing how energy works in buildings, I would say it's up to the community working on each project to best guide that project and say, in this instance, I think we really need to consider if no one comes to work and we have to run the electric heaters, what could that do? So good problems, always a good thing to have. All right, I'm going to share an example project that we worked on and sort of an indirect finding in the project that we found around some electric resistance. But we did a project looking at ERVs in, we're working with NYSERDA, kind of building on the work NEA has done, the Northwest Energy Efficiency Alliance, around high efficiency DOAS systems in the Northwest, and looking at, like, in other parts of the country, when would an ERV really help out to manage moisture if the climate had more humidity. But one of the pieces, a piece in that research that we got into was the challenge of frost that can build up in an ERV, and how in certain instances, when you have outside air that's very, very cold, touching these metal plate and frame heat exchangers, you can create ice, and certain strategies of products can use electric resistance to melt that ice. So you sort of have an electric heater. Depending on which product you buy, you may not have it on every product, but you could have this electric heating device. And just to kind of zoom in on when this happens, it really happens when there is water in the building. If we have humidity in the air inside, you can get this frost risk on the outside, leaving that heat exchanger. Arguably, I asked several manufacturers, do they design for this? And like, no, the buildings are just really dry. Which is perhaps true, though, in an age, again, post-COVID, we now have a better understanding that humidity in the air is an important thing to maintain. Some buildings may now have humidifiers. So we evaluated this problem from that worst case standpoint. What if a building was maintaining humidity at 30%? When would you get ice forming there? And so the thought is, like, if you can recover the moisture and pull it back into the building, it won't turn into ice. And so that's one benefit of an ERV compared to an HRV, is in these cold climates, you could avoid the need to run an electric heating device to melt the ice off. So just some charts of where frost would occur. This is just using some basic relationships on different energy recovery. What we see here is like latent heat recovery effectiveness. And then at what point would frost form on the coil? So essentially down here would be every HRV saying that if you had moisture inside your house or inside your building, 30% moisture, you would potentially get frost risk at 28 degrees. Whereas if you did a little bit of 40% latent recovery, that might drop to 12 degrees outside air, or 60%. Now you're down to like 2 degrees outside air. So we put that in our model as we assessed different packages and looked at it in different climate zones. And I realized in preparing for this that we had done this analysis looking at like the energy impact of this, but it's very much also a peak demand impact. So I went back and pulled these sort of runs out of the Rochester, Minnesota runs we did. And so what we're looking at is the heating system demand of the first system, which is an HRV only. And then the second row is the ERV. And the orange represents the heat pump that is heating the building. In this case, it was a bunch of mini splits heating each room. And then the red is that ERV's electric resistance component. So we can see this is a pretty cold day. It's always below, this week is like always below 30 degrees. But throughout, right, the HRV, the model was very basic, conservative, to say if it's below 32 degrees, assume the electric heat is on. You can see it almost nearly doubles the peak in some instances. Whereas this one down here, if it's doing some level of moisture removal, we can drop that limit to say 2 degrees. And now we would see a spike that's almost half. This is like 6.8 kilowatts compared to 11.6. So it's very conservative, right? Not all systems will control frost this way. There are other strategies. This is the one we evaluated because it doesn't impact air quality. Other strategies you often used will just shut off the outside air for 15 minutes and melt the ice. In this instance, we wanted to keep the fresh air going. But one of those things that I never really thought of as I modeled ERVs for a long time, like, could a system be selected after I recommend one of these products? And could that selection include a defrost control that is electric resistance? It's like getting into the details a bit on products, though it can now really have a big impact as we think about the grid. So the last thing I'll share here is we're doing some research now into HVAC thermal storage, and really looking at like heating hot water systems, not just for cooling. It's the more we study it, the more I realize that all the answers are really in all the great work that has been done around domestic hot water heating. It's this sort of language challenge and product and manufacturing challenge, I think, that we're hitting on what are simple ways to control large heat pumps and large water tanks? How do we size the two? Again, it's different load profiles and different levels of need, but a lot of the same solutions I'm finding are just sort of they've already been solved in water heaters. But in our project, what we were doing is right now we're hoping to have some findings. We looked at both load management, how could high performance envelopes and accounting for better envelope design or avoiding the worst envelopes designs reduce those spikes in peak heating demand. And then if we went further and added thermal storage, could we level out the demand? Could we avoid the worst times? What size tank would give us that shift for what size building and what size heating plant? So we're working a little bit on an analytical demo of a large office building and a large hotel as an example of what this would look like. But just as an example, we're talking about you can put thermal storage and HVAC systems on lots of different sites. So in this work we're thinking about it as a primary cold tank or hot tank of water, and then being able to avoid these peaks. This is the peak cost in California that we use in our simulation software, just again showing the magnitude of this summer peak 4 times the middle of the day and the winter peak again 3 times the middle of the day. So but that's kind of where we're going. These are just conceptual charts working through how could we think of systems that would both be heating the building, charging the tank, and then using that tank to either avoid the peak for a long period of time, or another concept, right, of just flattening the peak. Use the tank in conjunction with your heat pump and keep serving the building, but have that sort of flat profile. So with that, I guess my recommendations and conclusions would be recommending to really think about each project and the potential challenges that they could bring, the problems that each project might have. Weak spots, always consider those. Even through some research we've done, we found like in Australia, they even require code submissions to do these off-axis simulations where you have to submit 5 simulations where something isn't working right in the building. They don't have to achieve a goal, you just have to document what would happen. It's almost like educating the owner about the risk. And then I guess lastly, I didn't touch on it, but where possible, we are starting to use real measured profiles. So this is like some multifamily plug loads we were given. We normalize that. We help use that in our modeling today to try and give a little bit more of a seasonality or daily spike in how people use buildings. So nothing set in stone, but trying to augment a little bit of real data with the energy modeling data. That was a fly-by-night, but I will pass it back for questions here.
Well done, Neil, on trimming to bring us into time. Go back on video. So we've got about 15 minutes here for all of us to have a little panel discussion. We have a couple of questions in the Q&A. I have a couple of questions as moderator. Sometimes I get to flex my prerogative there, but I am happy to bring more in. I've seen a couple of questions related to sort of like the poking at questions around how long a shed might last. There was a question in the Q&A back from Molly's, would increasing the size of the hot water storage tank allow you to ride through more hours? And there was a comment in the chat that there was a little bit, made me think of the same thing, thinking about in Scott's head, did that load shift really work? It looks like there was still demand during the peak period, which was when we ran out of hot water basically and came back on. So I'm wondering if the three of you have thoughts on, given we're mostly talking about simulation, I mean, yes, a larger tank stores more energy, or a hotter tank is going to store more energy. If you have a mixing valve, you've got more juice and you can presumably, squeeze it longer, right? But I'm wondering if you have thoughts on getting a good handle on how much stuff, whether that's hot water or other capability, you might need to ride through an event of, say, 1 hour versus 4 hours. If you have thoughts on duration as it relates to sizing and simulation. And whoever wants to jump is welcome to start. I won't call on one of you unless I have to.
I can probably just jump in real quick and note that on the EcoSizer main sizing page, that tool has the ability to put in the shift period that you want to reduce or eliminate the electric resistance or the electric usage of the heat pump during, and then choose what percentile day you want to meet with that. So obviously, if there's a higher use day where there's more water being pulled out of the storage tank, you need more storage volume to meet that. But if you're looking for, a 4-hour period that's going to be met on the 90 percentile water usage day with 100 tenants, you can get that answer with the EcoSizer. One thing to note is that whether you're controlling for energy use reduction or demand charge reduction, your strategies might be a little bit different. So for energy use reduction, you might want to just try and turn off the system for as long as possible. Whereas demand charge reduction, you might want to figure out a way to modulate down or stage down things, but ride through the whole period. So that's just something to keep in mind when you're actually doing the design and writing the control sequences for projects like this.
I'll be brief, but I'll just comment, say exactly. Yeah, I think Scott hit it on the head there, especially in like large HVAC. I think you always need more storage than there's space or costs. Like location is the problem. So a lot of times I almost think the conservative step would be to just like ramp down and ride, like do a little bit of storage shifting every hour, but don't aim for the big peak because then you could run out of capacity. Something might not run right. So it will not nearly be as big of a peak reduction, but it would be the conservative step forward, I think, in the industry. If like that's how, at least in HVAC, we think of like load leveling first before we go to the deep reduction.
There was Molly, did you want to jump in?
Oh, well, not directly on that, but I did want to comment on the, I wasn't familiar with the work that Scott presented, and I thought that it was cool to see the assumptions about stratification in the tank, because in the Energy Plus model, for example, there's no thermocline. It's a single node in our model at a mixed temperature of the tank, right? So we're saying, we have this volume at this temperature and it's all usable, but that's not the reality of a real hot water tank because of that thermocline condition. So I thought that was really interesting.
Yeah, actually, Scott, maybe you could give us like a 1-minute overview of what it means to control to 2 or 3 different temperature points within the tank, because I think that's a useful construct here.
Sure. Yeah, so if you have a hot water storage tank, especially domestic hot water storage tank, you're going to have some level of stratification within that storage. So you might have cold city water coming into the bottom of the storage tank at 60 or 70 degrees Fahrenheit. You might be putting hot water into the top of the storage tank at 150. And so you're going to have that hot water is going to sit on top of the cold water. And there'll be a region in between those layers where you have a thermocline, where it's mixed, or there's heat transferring between the layers. And so it's not a perfect line hot water sitting on top of cold water. And so our strategy for getting the most out of the thermal storage tanks has been to basically, when we want to shed, we just look at a temperature sensor higher up in the tank where there's more likely to be hot water, because that's where the hot water is put in. That's where the hot water is being stored. And when we want to load up, we look at a temperature sensor down at the bottom of the tank so we can push the hot water all the way down. And it's really allowed us to get a much larger delta for hot water output than just changing the temperature set point of a single temperature sensor, maybe, kind of in the middle of the tank. In addition to that, it actually helps the kind of health, so to speak, of the stratification layer in the tank to be cycling the tank around like that, because you flush out kind of that mixed layer when you're loading up and shedding. Especially during the load up, you kind of push out that mixed layer. And that actually helps you keep a tighter stratification layer for longer, because if you're just looking at the temperature sensor in the middle, over time, the heat transfer between the hot water sitting on top and the cold water starts to make that thermocline layer just kind of grow until you have a big lukewarm region in the middle of your tank. And yeah, there's several reasons you don't want a big lukewarm layer. Load shifting being one of them, but I think that strategy of kind of cycling the tanks for load up and shed is helpful for a number of reasons, and it makes the stratification better.
Thank you. Quick question on what modeling software you're using, just for clarification, for all of us. That was a question. Ecosizer
everyone.
its own beast, but just a quick. Here's what we use.
I mean, that NEA project I showed was all run in Energy Plus using some prototype models, and then we detailed out the HVAC. And then we do a fair bit of design work in IES. And I had another example I didn't get to where we looked at peak reductions with IES. Same kind of exercise though.
Sorry, Energy Plus at PNNL.
Yeah. Quick question on cost and reliability. The question: what are the cost and reliability issues comparing central versus small in-unit heat pump water heater systems? And I'm going to tag on one piece to that that I have been interested in, which is about field maintenance of systems with relatively high pressure, like, for example, CO2 refrigerants. For colder climates, sometimes run at pretty high pressure. So I'm interested in your thoughts on reliability of systems. It's not really simulation, but it is an interesting question.
Yeah, absolutely. So in-unit heat pump water heaters, you just have a lot more many different pieces of equipment that can all have their own issues. And then someone has to go out, to that unit. It might be in the unit to fix it. I think central systems have reliability advantages in that when they're designed well, they work reliably, and you can put backup systems on them that's then going to serve the whole building. So if something goes wrong with one of your heat pumps, maybe you have electric backup system that you can run on while you're getting that heat pump fixed. I'd also say that central systems have some advantages in that you're not having that noise and cold air generating device at all the different apartments. So depending on how the architectural layout, that can be an advantage. And in colder climates, they're probably the better option for larger multifamily buildings, in my opinion. They're definitely better at demand response because you get to take advantage of the diversity of the tenant usage and manage that all in a central location. So if one person decides to take a really long shower when 20 other people aren't doing anything with their hot water, it's not going to trigger your system to use electricity.
Makes a lot of sense. Thank you, Eric. Glad you flagged that last piece. One of these questions says, so Neil, show the example. And I think we have answered the key things that for the most part. There was one question about cost frameworks and regionality of cost, but we kind of touched on that earlier. So Neil, if you want to take a couple minutes to show if there's still enough, if you have capability in 5 minutes here. we might be interested in. You're thinking the overheating piece? Is that what you're-
Yeah, but yeah.
I don't know if there is
I don't know. It's
ability
it's
for
not it's not vastly different from what I've shared. I guess what I'll just say is like we looked at on the envelope side, just like I'll just show one slide real quick. Like how far could you get if we were to think about like reducing, oh yeah, that's in here somewhere. I don't want to go through all of them. That takes forever.
yeah. This works fine for the
Far too long. But it's more thinking about like this. A lot of this is all I would say. This is just research that A2 did on our nights and weekends, thinking about solar gain and how Passive House is really built for like cold climates. A lot of great metrics there. A lot of challenge when we start to think about hot climates. And so I always had this thought of like, well, we know solar shading works. We know there's like low E surfaces, roofs and walls. How far could we go? Like if we put these into buildings, and we really studied this actually from a heat stress perspective. So if you had no AC, what do you get? Like, can you avoid heat stress in buildings? And then conversely, right, if you run your cooling, you get a benefit. So this was looking at if we went with an existing building, building built a code and then identified, let's add shading, let's pick some low reflectivity surfaces. What's the cooling reduction? And you basically see in a multifamily building, this is all modeling again through IES. The biggest step change just from going from that 2004-esque building to a modern building, lower solar heat gain, the biggest step change in demand. This is our evening lights kicking on. I kind of put it at the top of the chart just to show how that one challenge can sort of be a third of the cooling. And then further, like the high performance envelope, it did show a peak cooling reduction, not as substantial. However, there are other benefits that come with this. That building was able to avoid, if no cooling is running, it's only 89 degrees inside, whereas the other buildings were in the 90s. So thinking about multiple benefits that can be achieved as we think about cooling strategies. So that was our other example. So
That sounds like passive survivability to me.
There it is.
Which gets me to one closing thought that I think is a great segue to something I love thinking about. We run an energy model and we get an 8760 or 15-minute lead data set, a bunch of kilowatts out of it, right? You get a load shape of some kind. Traditionally speaking, that's what I think of as one of the real primary output reasons to do it. And then we translate that into other stuff. We'll say, hey, like with Molly, hey, here's these ASHRAE time of use rates, or we say, this is what it means for energy savings, peak demand, et cetera. We can look at coincident peak demand. But that also can tell us some other things like resiliency. And so I think having the construct that we can use energy models and energy simulation to predict some of these non-energy benefits, even like, hey, this building can coast longer when the cooling is out. That is passive survivability. That's a resiliency benefit. And we can use these model outputs to predict those really important non-energy benefits. That might be greenhouse gas, that might be resiliency, that might be dollars. There's different things we're interested in getting. But I think it's increasingly important to start thinking about some of that other stuff. And sometimes that's what drives the decision just as much as the energy savings or the operating cost. Some of those other benefits that in the most traditional sense seem like sort of side details. Sometimes that's what makes the decision go. With that, I want to thank all three of you very much for spending the last 90 minutes with us, and for everyone who's on the line, the 50+ people who joined us today and stuck with us this whole time. Thank you so much for your time. This has been recorded. We do expect to post the slides in PDF. And if you want a continuing education certificate, reach out to us, info@newbuildings.org. We'll make sure that happens. I'm going to put a note in the chat about that right now. Thank you so much, everybody.